So you've just fabricated your best performing solar cell, and now you want to know everything about the charge carrier dynamics, where and how they recombine, the trapping rate, and so on. Transient photoluminescence measurements contain all the information you need in just a single curve. You just need to extract it. Hello and welcome to Fluxim Science Shorts with me, Dr. Antonio Cabasvidani. Before we get started, make sure you subscribe, like, and hit that notification button. Transient photoluminescence, also called time-resolved photoluminescence, is a measurement technique used to determine the recombination dynamics in a light-absorbing material. Shining a short laser pulse generates charge carriers. The carriers that recombine radiatively cause the emission of photons from the sample, and photoluminescence can be measured until recombination ceases. To extract information, you can fit the TRPL decay with a bi-exponential equation, which gives you two lifetime values for the charge carriers, the radiative and the non-radiative lifetimes. Great, right? But you're not quite finished. Lifetime values depend on many other parameters that influence each other as well. There's illumination conditions, recombination coefficients, doping of the absorbed material, charge extraction, carrier mobilities, trap density. It is actually difficult to say with certainty. However, there is help at hand. 1D drift diffusion simulations can help you. The equations defining the drift diffusion can describe the movement of the charges in the solar cell after the photoexcitation. Exactly what you need to understand the dynamics of the charges in your sample and interpret the TRPL. Here at Fluxim, we analyze what influences the TRPL decay of a perovskite layer with SETFOS, a 1D drift diffusion simulation software which includes mobile ions and a user-friendly interface. Broadly speaking, the shape of the TRPL decay depends on the radiative and non-radiative recombination rates of the photogenerated charge carriers. By sweeping the illumination intensity, we vary the amount of photogenerated charge carriers, which influences the initial curvature of the decay. In fact, the radiative recombination has a quadratic dependence with the density of the photogenerated charge carriers. If instead we sweep the capture and emission rates of the charges, we see a change in the tail of the TRPL decay, because we are varying the non-radiative recombination rate, which affects predominantly the slope of the long tail, and has a linear dependence with the photogenerated charges. So how to set the right properties and illumination conditions? It is actually not that straightforward, and it might require some guessing. But after a lot of testing, we want to share a fitting routine that we believe is instrumental for setting a reliable and realistic TRPL simulation. It starts by setting the electrical properties of the light-absorbing material. Then, you choose a range of values within literature for the radiative recombination coefficient. It is difficult to precisely quantify it, so you should test the simulation with multiple radiative recombination coefficients. At this point, you should sweep the illumination intensity. The goal here is to find the intensity that reflects the experimental conditions and gives you a good fit for the initial curvature of the decay. Eventually, you can fine-tune the electrical properties set at the beginning to fit the long tail of the decay. How do we know that it works? I'm going to show you. For a good fit between simulated and experimental TRPL, we first set reasonable electrical parameters. The radiative recombination coefficient for perovskite is within 10 to the minus 10, so we chose the lowest and the highest extremes of such range. The results after the illumination sweep are clear. The highest radiative recombination coefficient is the right one, and the simulated curve fits the experimental one for a light intensity within the experimental range. The long tail will fit after minor adjustments of the electrical properties. Would you like to try the following routine? Visit us at fluxim.com and request a free 1-month SETFOS trial or simply scan the QR code. Thanks for watching, and if you have any questions, please leave them in the comment section below.